Let's have some fun exploring this bouncing problem. Again, what we have is a metal bullet and a rubber bullet that both have the same mass that are fired at a log. Both are going to hit the log with the same initial linear momentum, but when the metal bullet strikes the log, it's going to penetrate the log and basically come to a stop somewhere inside the log, whereas when the rubber bullet strikes the log, being made of some sort of elastic material, the rubber bullet's going to bounce off and travel back in the direction it came from with the same speed that it hit the log with. And so the condition we're going to impose on this problem is that the time interval that it takes the metal bullet to be stopped by the log, as the metal bullet travels through the log and gets lodged in the log and comes to a stop, there's going to be a certain amount of time that takes to happen. That time interval is going to be the exact same time interval that it takes to reverse the motion of the rubber bullet once it hits the log and goes back the way that it came. And if that's the case, if those two time intervals are the same, the question we want to answer is which bullet is more likely to knock over the log. So let's begin by drawing an x-coordinate axis that's parallel to the ground and positive to the right. And we know both bullets have the same mass. Let's also assume that they strike the log with the same speed v0, both heading towards the log. Well, from Newton's third law of motion, we know that the force that the bullet exerts on the log is going to have the exact same strength as the force that the log exerts on the bullet, but in an opposite direction. And if we let our system be a bullet and we apply our impulse momentum theorem relationship, the net impulse that the bullet experiences when it travels or interacts with the log is going to be related to the change in the linear momentum that the bullet experiences due to that interaction. The net average force the bullet experiences as it interacts with the log is going to be related to that net impulse it receives from the log divided by the impact time delta t, or the change in the linear momentum of the bullet as it interacts with the log over that impact time delta t. And again, for both bullets, delta t is going to be the same. Delta t for the metal bullet is going to be the amount of time that it takes the bullet to strike the log and come to a stop. And delta t for the rubber bullet is going to be the amount of time that the rubber bullet interacts with the log as it strikes the log, comes to a stop, and then turns around and goes back the same way due to the bouncing effect. What we have an interest in is determining the net average force that the log receives. And that's going to be the same magnitude as the net average force that the bullet receives as it interacts with the log, but in the opposite direction. And if we can calculate the change in the momentum of a bullet as it interacts with the log over the time that the bullet interacts with the log, then we can relate this change in linear momentum of the bullet and the bullet's interaction time with the log to the net average force that the log experiences. And so the bullet that creates a larger change in linear momentum is going to be the one that is able to deliver the larger average force to the log and will be more likely to knock the log over. So let's look at what the metal bullet is doing. The metal bullet starts off with an initial velocity of v0 times I hat is traveling in the positive x direction, but when it gets lodged in the log, its final velocity is going to be 0. And we can easily calculate the change in the linear momentum of the bullet that's made out of metal by multiplying the mass of the metal bullet by its final velocity and subtracting from that the mass of the metal bullet times its initial velocity. And since the final velocity of the metal bullet is 0, as it gets stuck in the log, the total change in the linear momentum of the metal bullet is just going to be minus the bullet's mass times its initial speed times the I hat unit vector. The rubber bullet is a little bit different. It has the exact same initial velocity as the metal bullet, but due to the fact that it's going to strike the log, interact with the log, and bounce back, its final velocity is going to be in the negative x direction, and we're going to assume that that rubber bullet travels away from the log at the same speed that it travels towards the log. So if the bullet was traveling 300 meters per second towards the log, when it was striking the log, it's going to be traveling at 300 meters per second away from the log as it bounces off. So when we calculate the total change in linear momentum of the rubber bullet, we'll have to multiply the mass of the rubber bullet times its final velocity, and then subtract from that the mass of the bullet times its initial velocity. And what we'll get is -2 times the mass of the rubber bullet times its initial speed times the I hat unit vector. And it should be readily apparent, since both bullets have the same mass m and the same impact speed v0, that the rubber bullet has twice the change in linear momentum than the metal bullet. As a result, this larger change in linear momentum that the rubber bullet has is going to exert a larger average net force on the log. Thus, that larger net average force that the log experiences from the rubber bullet is going to make the rubber bullet a lot more likely to knock over the log than the metal bullet. So bouncing definitely has a significant impact in these types of interactions of, in this case, a bullet with a log. The final question we want to consider is one that involves two hammers and the forces these hammers can exert on nails. In the first situation, we've got a massive 5-kilogram sledgehammer that we're going to use to push on a nail. And in the second situation, we've got a lightweight 0.5-kilogram claw hammer that we might use around the home to put nails into a wall to hang pictures. But with this hammer, we're going to swing it with a speed of 6 meters per second down towards a nail. And as that hammer makes contact with the nail, it's going to interact with the nail for a period of time equal to 1/1000th of a second. So in both these situations, we want to calculate the average force each hammer exerts on its respective nail as we try to push the nail or drive the nail through maybe a piece of wood. So for situation A, let's just imagine you push on the sledgehammer by placing the head of the sledgehammer down on top of the nail, and then you basically lean into the sledgehammer with all of your body weight, and if the total mass of your body weight and the sledgehammer together is about 100 kilograms, and we're trying to apply some sort of weight force to that nail via the head of the sledgehammer, then this mass times roughly 10 meters per second squared for the acceleration due to gravity is going to result in about a 1,000 Newton downward force that we're able to apply to the nail. So in this case here, the sledgehammer is able to push on its nail with a downward force of about 1,000 Newtons. For the next situation, with the claw hammer striking the nail, we're not going to be putting our body weight behind the claw hammer per se. We're going to be swinging the claw hammer with a speed of 6 meters per second in the downward direction. And so if I want to figure out what's the net average force that the hammer is going to experience as the hammer strikes the nail, I can figure that net average force out by looking at the net impulse that's applied to the hammer, or the change in the hammer's linear momentum vector over the time interval during which the hammer makes contact with the nail. And if I look at the change in the linear momentum of the hammer, that's just the difference in the hammer's final linear momentum relative to its initial linear momentum. And if I know the mass and the final and initial velocities of the hammer, I can figure out what this net average force is going to be. The hammer's got a mass of 0.5 kilogram, and its final velocity turns out to be, well, the hammer comes to rest after driving the nail, and let's say the hammer is moving down. Even though the average or the final velocity is 0 meters per second, or the final speed is 0 meters per second, let's assume that the velocity is going to have a direction that's associated with the downward motion of the hammer. And then likewise, the initial momentum of the hammer is going to be its mass times its 6 meters per second speed in the downward direction. And when we divide that momentum difference by the impact time that the hammer makes with the nail, we'll find out that the average net force that the hammer experiences as it interacts with the nail is negative 3,000 newtons in the downward direction, or since minus down is the same as the direction up, it'll experience a 3,000 Newton force up. Well, that's what acts on the hammer. We want to know what type of force does the hammer exert on the nail. And so in this case here, by using Newton's third law of motion again, the average net force that the nail experiences from its interaction with the hammer is going to have the same magnitude but the opposite direction of the average net force that the hammer experiences. And so if the hammer experiences a 3,000 Newton force up from the nail is going to experience a 3,000 Newton force down from the hammer. So the interesting thing about this is that the small, lightweight claw hammer exerts a much, much, much larger force than the large, massive sledgehammer. And this is in due part to the fact that even though the claw hammer has a small mass, the faster we swing the claw hammer and the smaller the impact time the hammer makes with the nail, the larger the net force the hammer is going to experience, and consequently, the larger the net force the nail's going to feel from the hammer. So that wraps up everything in topic 6-1. As always, review what we've talked about and enjoy your physics.